Whoops, starting already. All right. So today, gentlemen, we're going to move on with section 14.2, which deals with restoring forces and simple harmonic motion, specifically linear restoring forces. You'll remember that from yesterday that the restoring forces for the marble and the bowl were always pointing toward the bottom of the bowl, but they weren't linear because obviously the bowl was curved. Here, we're going to concentrate on linear restoring forces and specifically how they affect simple harmonic motion. So let's say that we have a mass attached to a spring on an air track. It's simply on an air track to prevent the force of friction from playing any role here. So if the spring is at equilibrium with the mass and everything's hunky-dory, there's no net force here. The spring is not pulling the block in or pushing it outward for that matter. Then we apply some kind of force to this so that it moves from the equilibrium point out to this point here, all right? At that point, the spring is now going to be exerting a force back on the block to restore equilibrium in order to bring it back to that equilibrium point. All right, so this is going to be identified as the force of the spring. Now, in order to calculate the value of that force, we're going to use Hooke's law, which is again shown here. All right, the net force acting on the block is going to equal the negative times K, which is the spring constant of this spring, times the displacement. And the negative sign tells us that it's a restoring force because the force is in the direction opposite of the displacement. All right, if you pull the glider to the right, X is going to be positive. If you, because the force is to the left, back toward equilibrium. It's a linear restoring force because it's simply moving in a straight line back and forth, and the net force is toward the equilibrium position, and it's proportional to that distance from the equilibrium. All right, so when you displace an object from its equilibrium position and the force pushing it back toward equilibrium is the resulting motion is simple harmonic motion. The answer is, of course, linear. All right, linear. All right, because you push one way, it pulls back the other way. Okay. Now, how do we determine how far this thing is going to move during an oscillation? Well, we call that an amplitude. All right, abbreviated with a capital A. Amplitude is defined as the object. What in the name of all that is holy? The amplitude A is the object's maximum displacement from the equilibrium. So if the zero line right here represents equilibrium, this distance is the amplitude. And of course, notice that on the other side, it's the negative amplitude, okay? And so if this is the equilibrium point and I move the block this far, it's then going to move back this far before going back to the equilibrium point. So the oscillation is taking place about that equilibrium position. All right, it's going back and forth, each time going across the equilibrium position. And it's doing so in this case with a linear restoring force. The same kind of thing is true when you hang a mass on a spring. So now we're talking about vertical positioning. Okay, for a hanging weight, the equilibrium position of the block is where it hangs motionless. All right, the spring is stretched by a distance L. So here's the unstretched spring. All right, and so that's this distance here. But then this distance from here to here is the amount that we've stretched the spring. Okay, now the block itself has a mass of W. A mass of M, which means that it has a weight of W. And if the block is stationary, that means that the force of the spring pushing or pulling upward is equal to the weight pulling downward. So, according to Hooke's law, the force of the spring is going to equal the spring constant times that change in the length of the spring. And we can rearrange this. Well, we know that the net force is going to equal the force of the spring plus W, and we're going to set that equal to 0. Why? Why? The force of the spring is equal to the spring constant times the displacement, and the weight, of course, is equal to m times g. Now, if I simply take this portion of the equation and rearrange it to solve for delta L, I end up with this formula: the length of the spring at the equilibrium position for a vertically hanging mass on a spring. Now, if we push the block up above the equilibrium position, the spring is still going to be stretched by an amount that's equal to delta L minus some value y. And here, right here, is the value y. And so therefore, the net force on the spring in this case is going to equal the net force is going to equal the spring force plus the weight. Well, the spring force in this case is the spring constant times the delta L minus y value minus the mg here. If I distribute the k to both terms, it's k times L and k times negative y, all right? And then mg is all by its lonesome. And then I use the commutative property of addition to rearrange that. I get k times delta L minus mg minus ky. But I know that this term is equal to 0, and so now the net force is simply equal to negative ky, which, if you are a clever little AP Physics student, you will realize is simply another way to write Hooke's law. Now, gravity plays a role in this as well. The role of gravity is to determine where the equilibrium position is, but it doesn't affect the restoring force for the displacement from the equilibrium. And because it's a linear force, a mass on a vertical spring will still oscillate with simple harmonic motion, up and down and up and boingy, boingy, boingy. All right. In this case, the weight pulls down, the force of the spring is less because it's not stretched as much, and so there is a net force pulling the object downward, and so it'll restore and bounce back and forth each time crossing that equilibrium point. A pendulum is also an interesting aspect or an interesting phenomenon to study in terms of simple harmonic motion. It's just a mass suspended from a pivot point by a string or a rod or something like that. So if we were to measure the angle of displacement here and call it theta, the length of the pendulum is L, the mass of the bob of the pendulum is M, and the arc length is S. Well, for very small angles, L and S form a right triangle. And so we can use the laws of trigonometry in order to analyze this. Now, the pendulum itself is indeed swinging along a circular arc. But there's still a net force on this. So there's tension in the string, there's the weight going down, and this is the restoring force. But we realize, based on our work, that restoring force is equal to the weight times the sine of theta. So the net force here is going to equal the weight, which is equal to negative mg times the sine of theta. All right, so that's the tangential component of the weight, and that's the restoring force in this case. The equation can be simplified for very small angles because the sine of theta will approximate theta. All right, this is a math thing that you should have learned and it's called the small angle approximation. And therefore, the restoring force, instead of being mg sine theta, is just mg theta, negative mg theta. But since theta is the opposite S over the adjacent L, we can replace that with the arc length over the length of the rod. And so that gives us this term as the net force on a pendulum. And so the force on a pendulum is a linear restoring force for small angles. And so the pendulum will undergo simple harmonic motion, back and forth, and back and forth. All right. Your homework, gentlemen, for tonight is to do questions 1.5 at the end of chapter 14. I will collect this homework assignment, and it will be due on, when will it be due? Wednesday at by 2. I would like it by Wednesday at 2:30. All right. Thank you, gentlemen, and have a good day. Oh, follow the directions for submitting the homework that are listed on today's topic page in the portal.